Hi, this is Kamakura. In this tutorial, I'm going to show how you can use my analytics tools to run a principal component analysis, how you can reduce a large number of correlated variables into a few principal components or latent factors that summarize the information contained on those original variables. Before doing that, I'm going to try to give you an intuition behind principal component analysis. In this sheet, I have 50 countries described by three variables: electric power consumption in kilowatt hours per capita, household consumption per capita, and health expenditure per capita. And to give you the intuition behind principal component analysis, I'm going to plot those three variables using my 3D scatter plot. And what you can see in this map is that even though we are plotting the countries in three dimensions by health expenditures, electricity consumption, and household consumption, you can see here that the countries seem to be more or less aligned in a single dimension. If I rotate it a little bit, you can see here that there is a line that pretty much describes those 50 countries. A line that would look more or less like this blue arrow that I drew on top of the chart. And that would be what we call a principal component that reflects the fact that household consumption, electricity consumption, and health expenditures are correlated. So that even though we are trying to describe those countries along three dimensions, in reality, those three dimensions are captured by that single line that reflects their socioeconomic development. And that's the basic idea behind principal component analysis. Try to capture with a few components most of the information contained on a larger number of variables. And that's possible whenever the variables show some pattern of correlation among themselves, which is typically the case with socioeconomic data. For a better understanding of principal component analysis, let's look at another application. In this application, we have survey data from a survey conducted among small business owners who have applied for this specific credit card targeted towards business people. And each one of these small business owners were asked to rate multiple reasons to apply for this credit card on a 10-point scale, where 0 meant not at all influential and 10 meant extremely influential. So for each one of these business owners, we have 10 columns representing the extent to which each one of those 10 reasons was influential or not in the decision to apply for this credit card. And I have calculated the correlation matrix among each pair of reasons. And this is what we have here. And you can see that some of the reasons tend to be highly correlated. For example, a competitive annual percentage rate is highly correlated with a competitive credit limit amount. In other words, small business owners who found the annual percentage rates to be important also found the credit limit amount to be important. Here we have a very high correlation. No blackout dates and ability to fly any airline. Correlation of 0.94 across 383 observations. Small business owners who found no blackout dates to be highly important also found the ability to fly any airline as also being influential in choosing a credit card. It's hard to find a pattern in this data, but as soon as we rearrange the rows and columns, that pattern becomes more obvious. Here it is. The only thing I had done here was to rearrange the rows and columns so that variables that are highly correlated with each other are grouped. So now you can see fairly clearly there are two blocks of variables here. We have one block that I called factor 1 that contain competitive annual percentage rate, competitive credit limit amount, competitive annual membership fee, ability to transfer your previous balance, and so on and so forth. In another block, highly correlated among themselves that include ability to fly any airline, no blackout dates, no seat restrictions, ability to redeem miles for a ticket. You can see that we have two blocks of variables that are highly correlated with each other. Like in our previous example, for where we have three variables that essentially align the data on a single dimension, what we have here is a set of 10 variables that are fairly contained within two dimensions, which we are going to call factor 1 and factor 2. So what is the main goal here? The main goal here is dimension reduction. We wanted to reduce a large number of variables, in our case is 10 reasons to apply for a credit card, into a few factors or components that capture most of the information contained in the original variables. So we want to be able to capture with only a few factors. In our example, two factors. We wanted to capture as much as possible of the information contained on the original variables. And what allows us to do that is effectively variables are correlated with each other, and they are correlated in sets. So the intuition here is that we are trying to capture most of the information contained in the original variables with a few summary variables or factors or components. And the idea here is that variance is information. So we are trying to capture that variance, as much of the original variance in all the variables, with a few factors. And covariance or correlation is redundancy. The fact that few variables are correlated with each other means that they're pretty much carrying the same information. So we are trying to capture as much of the information contained in the original variables by eliminating that redundancy, capture the essence of the information contained in the 10 variables with only two factors by avoiding redundancy. Looks like we need at least two factors or components to capture the essence of the reasons for getting a small business credit card. As I did before, I call them factor 1 and factor 2 for the lack of any better name. So we're going to assume that each customer has these two scores, that all the data really conveys information on two latent factors or two components, so that each customer has scores on each one of those two components, one for F1 and one for F2. Then what we observe, the answers to the 10 questions, are consequences of those two factors, those two scores, the sentiment of the customer along those two dimensions, F1 and F2, is what drives them to answer those 10 questions in specific ways. So mathematically, we wanted to represent what we know, the answers to the 10 questions, as a combination of the two unobserved or latent factors or components. And the reverse is what we are trying to accomplish. We are trying to figure out what are those two latent factors that cause consumers to answer those questions, the 10 questions, with a certain pattern. So F1 and F2 are the scores that each customer would have on the two dimensions. The factor weightings and loadings are the weights that are applied to the factor or components to produce what we observe. So what we observe are the ratings on the 10 reasons to apply for the credit card. Now we're trying to figure out, given what we observe, what are the factor scores F1 and F2, and what are the weights that apply to those scores would result into what we observe. And because those variables are correlated, what we expect is that certain variables would have heavier weight on one factor, while other variables would have a heavier weight on another factor. And mathematically, what principal component analysis does is to estimate those weights and also to obtain those factor scores, F1 and F2, for each customer in this case. A few more details about principal component analysis, which is also called factor analysis. By default, all variables are standardized. That means that each one of the variables has a variance equal to 1, as if each one of those variables enters the analysis with 1 unit of information. As I mentioned before, variance is information. So we are standardizing the information so that each variable enters our analysis with 1 unit of variance or 1 unit of information. Since our database has 10 variables, that means that we start with 10 units of variance to explain up to 10 factors. Since we have 10 variables, the most we can explain is 10 units of variance by using 10 factors at most. Of course, with 10 factors, there is no space reduction. We are not summarizing anything. We hope that we can, using only a few factors, 1, 2, 3, explain most of the 10 units of variance in the original variable. Each factor or component tends to capture the most possible of the original units. In other words, the first factor is going to capture as much information as possible on the original data, as much of the 10 units of variance in our particular example. Then the second factor is going to explain whatever is left out. Because the first one tried to explain the most, you should expect that the second factor is going to explain less because there's less to be explained, and so on and so forth. And the amount of standardized variance captured by each one of the factors is called eigenvalue. And the sum of the eigenvalues, if we keep all the 10 factors, all the 10 possible factors, will be equal to 10. And we expect the first factor to capture as much as possible of these 10 units, the second to explain slightly less, and so on and so forth. And if we plot the units of variance explained by the first, second, and third factor, we see these diminishing returns to scale. And typically, you're going to see that beyond a certain point, it's not worth retaining more factors. And that leads to a rule for deciding how many factors we need. So in our example, the first factor captured 3.7 units of information, which is 37% out of 10. Second factor explained 2.4 units. So the top two factors explain already 61% of the original information. One of the rules, it's called the elbow rule. The elbow rule says that you should stop adding factors when there is an elbow in the plot. And the reason for stopping before the elbow is because if we go ahead and add the third factor, logically we should also keep the fourth and fifth because they explain only marginally less than the previous one. On the other hand, between the second and third factor, the second factor certainly explains a lot more than the third. So we should stop before the elbow because if there is any reason to add the third, that same reason should dictate that you would keep the fourth, the fifth, and sixth, etc. That's the elbow rule. The other rule is the unit rule. Is to stop adding factors when the eigenvalue drops below 1. And what is the rationale for that? We don't want a factor, a summary variable, that contains less information than any of the original variables. If you recall, since the variables were standardized, each one of them entered the analysis with 1 unit of information. So we don't want to add any factor that contains less than 1 unit, and that's the unit rule. With 2 factors, here are the factor loadings or factor weights. And as I have shown before, we got something that we should expect. Some of the variables, competitive annual percentage rate, competitive credit limit, competitive annual membership fee, ability to transfer your previous balance, they load on the same factor. While other variables, ability to fly in the airline, no blackout dates, no seat restrictions, they load on another factor, which means factor 1 captures the information contained in ability to fly any airlines, no blackout dates, no seat restrictions. So the meaning, the information contained in factor 1 is the information contained on these variables. And that is something that we can use to interpret factor 1. Same thing for factor 2. So instead of calling them factor 1 and factor 2, now we can use those weights to give them a more proper name. For example, factor 1 seems to be more related to perks. What do you get as perks from the credit card? While factor 2 seems to be more about performance, financial performance of the credit card. And here's a plot of the factor loadings. This is nothing more than a chart of this table. And here we find something interesting, is that factor 1 and factor 2, which are the vertical and the horizontal axis, they don't align perfectly with the variables. But if we could rotate somehow all the red arrows by about 5 to 10 degrees, then you would see the arrows pointing to the east, southeast, would be pointed more towards east. Same thing if we rotated the vertical arrows by about 5 to 10 degrees to the left, then they would align almost perfect with the north axis. And that's what we call factor rotation. Here's the original solution, and you can see that there is a certain angle between the horizontal axis and those variables. There is more or less the same angle between the vertical axis and those variables. So the variables are not perfectly aligned with factor 1 or factor 2. But if I do a slight rotation of the map, mind you that I did not change the map at all. I rotated everything by the same angle. But what that accomplishes is that now the new factor 1 and factor 2 would be almost perfectly aligned with one set of variables. And that's what we call a orthogonal factor rotation. And again, it does not affect the ability of the two scores to explain the observed data. Okay, nothing is gained, nothing is lost in terms of information. The only thing that this rotation accomplishes is improving the interpretability of the factor scores. And here's the rotated factor loading. Now you can see that the loadings are more clearly aligned with factor 2 here and factor 1 here. And here's the final rotated solution. To see how you can run a principal component analysis on my analytical tools for Excel, let's open my analytic examples and look for the principal component example, which is on a separate tab here. And what we have here is a collection of 65 countries described by 36 socioeconomic variables. And what we want to do here is to reduce these 36 variables into a few principal components so that we can describe the 65 countries in terms of these 6 socioeconomic factors or components rather than using the 36 original variables. Hopefully, what we can accomplish here is to reduce those 36 socioeconomic variables into a few components that provide a better summary of the profile for the 65 countries. To do that, let's go to Add-ins, Kamakura Analytic Tools, Principal Component Analysis. And you can see here that you can analyze a maximum of 100,000 rows and use a maximum of 150 variables or columns. The data is already highlighted. Click OK. And let's ask for 6 factors. We always want to rotate the components because that improves our ability to interpret these components. And rotating does not affect the ability to explain the original variance in the 36 variables. And let's get a plot of the first 3 dimensions. Let's start with the factor loading. So what we have here are the eigenvalues first. So remember, we start with 36 variables, so we have 36 units of variance to be explained. The first factor explained 10 out of these 36 units. The first 2 factors explain about 15 of those original units. And the first 3 factors explain about 18 of the original 36, about half of the variance contained in the 36 variables. And what we have here in red are the factor loadings for each one of the variables on each one of the factors or components. And in blue, we have the factor scores for each one of the countries. So a summary score for each one of the countries on the 6 dimensions. To interpret these 6 dimensions, Let's look at least for the first three factors, let's look at the charts. This is a chart that plots the factor loadings for each one of the 36 variables on the first and second dimensions. Let's look at the first dimension. Move things around so we can read them. Let's see what correlates heavily with the first dimension. The first dimension is highly correlated with survival to age 65 for males, survival to age 65 for females, life expectancy, and correlates negatively with mortality rate for adults female and mortality rate adult male. Looks to me at least, that the first dimension captures longevity. What is on the second dimension? It correlates heavily with armed forces personnel as a percentage of total population and military expenditure as percentage of GDP. So the second factor seems to capture some kind of military power or investment. Let's look at chart 2. Chart 2 plots the factor loadings for the first dimension, which we already interpreted, against the third dimension. Let's see what correlates highly with the third dimension. Gross savings as percentage of GDP, population density, trade as a percentage of GDP, and GDP growth, and correlates negatively with consumption expenditure as percentage of GDP. So this third dimension seems to be related to economic growth. Now we can plot the countries on those three dimensions, and I'm going to create a new tab with the score for the country. And if you recall, okay, I interpret the first dimension as being longevity, the second military, and the third economic growth. So let's get a plot. So this is a summary of the 65 countries on the first three components. Kamakura Analytic tools, 3D scatter plot, reduce the font a little bit. There you can see that the country that invests most on a per capita basis in military is Jordan. The countries with the highest longevity, this is military expenditure. Here we have longevity. And here's economic growth. We have Singapore, Cyprus, South Korea, Greece, and which countries do better on economic growth. We have Singapore, Thailand, Bangladesh in the economic growth dimension. This is how you can do principal component analysis using my analytic tools for Excel.